although this video shows the uniform cost search and explains priority queue, you might want to use a different algorithm. So stay to the end of the video if you really want to know which algorithm is the one that you actually want. Uniform cost search, UCS algorithm. Let's have a look at an example. We've used this tree a lot so far. Now we perhaps wouldn't use a tree for uniform cost search, but we can just explain it here. We have the nodes as we did before, we have the edges that join the nodes, but here we have a cost, like a value from the path from one node to another. So for example, 1 to 2 is a value of 1, 1 to 9 a cost of 5, 1 to 10 a cost of 3. So you can see here we've had these digits to represent the cost from going one node to the other. So the idea, we want to find the shortest path to a node, and we implement this with a priority queue. Now these are the shortest paths, and how do we get these results? Let's quickly look. So here is our tree. We look at the nodes 2, 9 and 10. We have value 1, 5 and 3. So you can see our cost getting from 1 to 2 is 1, 1 to 9 is 5, 1 to 10 is 3. Simple. Now the next values, the next nodes are 3 and 4. Now we can see, if we see the cost from 2 to 3, now the cost from getting to the root node, to node 3, is 3, 1 and 2. So the path is 1 to 2 to 3 and the cost is 3. And node 4 will have a cost of 5 because it's going from 1 to 2 to 4. So can you see that the path from the root node will have a cost? To finish off, we have nodes 5, 6 and 7. We can see the cost of getting to 5 from the root node is 6. Node 6, we have a value of 7 for the cost, and 7 there is a value of 8. And of course we have the last node 8, which has a cost of 2 from the node 5, but from the cost from the root node would be 8. So we've gone from 1 to 2 to 4 to 5 to 8. 1, 4, 1, 2 is a total of 8. So this is an algorithm looking at the shortest path or least cost, and we normally apply it on a graph. Here's the results that we showed before. So now let's have a look at the code. Here we've got the graph, or the tree, which tree is a graph essentially, and we've added the edges, and also with the numbers we've got the first node to the second node and then the cost in the brackets. And here's the actual code. Let's have a look in the editor. Here we have our code in the editor, the graph that we've defined and used in the example, which is the tree. And here we're going to pass the graph, start at node 1. We're going to see if we can find node 8, meaning we're going to go through the whole tree. So you can see the code here, and if we run it, you can see the different paths. So path to node 1, 2, 3, 10, 4, 9, 5, 6, 7, 8, and here's the values of the path from the root node to that node. And at the end we did find node 8, so the target was found. So that's the code for the uniform cost search. We can see here the output of our code and the example we used in the slides. How about a task for you to work out? Now, rather than a tree, we're going to apply this algorithm on a graph. What is the cost from the root node 1 to each of these nodes? Let's give you an example. The node 7, we can go from 1 to 5 to 7 with a cost of 3. There are other routes, but this is the shortest path. So that's an example. What about the other nodes? You should be able to work it out. Okay, here's some questions. Uniform cost search is a variant of Dijkstra's algorithm. Well, what is Dijkstra's shortest path algorithm? Uniform cost search is implemented with a priority queue. Well, what's a priority queue? Let's explain both of these. Dijkstra's algorithm. Now, we've actually seen this before, but here's some uses of the algorithm, essentially looking for quickest routes or shortest paths, or minimizing time, or navigating efficiently. So we can see different areas where it's used. Network routing is the area that I personally would teach it to students when they learn about networks and routing in networks. So we don't need to go through all the details about how we might abstract or get the shortest path from using a graph, but here we have the example that we've used previously, where we have nodes, or in a network we have routers, and we've given them a name, U, V, W, X, Y, and Z, and then there's a cost from each node using an edge and a cost on that. So with Dijkstra's algorithm, you can see we can work out the minimum cost, like the shortest path to each of the nodes. So we'll have a look at the Dijkstra algorithm later on in this video. Here's the code, but we'll explain it more later. Now, uniform cost search, yes, we know it's a variant of Dijkstra's algorithm and it's used in AI, and it's very good for looking at graphs not very large or even infinite, because we're looking at the path iteratively as we're going through them. So we don't need to go through the whole range as we might do with a depth first search, for example. So this is where we can use uniform cost search. Where it's used, quite similar to what we've already seen with Dijkstra's algorithm, perhaps not as many different uses, but examples would be using in AI search algorithms, for example. Now, what about a priority queue? The primary queue is a bit like a list. We put values in. The difference is that when we get the values out, we want them in order. So we can see with this program, you can see with the queue that's been converted into the list, so we can see it, the numbers are not in order. But when we get the values are retrieved, printed in order. That's a priority queue. They can be used to store values a bit like a dictionary. So here we've got some cities and we've given them a value, and you can see when we print that they're not in order, but when we use a loop and we want to retrieve each value, then it retrieves them in the order 1, 2, 3, 4. So priority queue, meaning we store the values, but when we retrieve the values, there's a priority order, and that's how they're retrieved. How do you get on with the task? Well, let's check the solution. Here we had our graph, and we've got the costs for 2, 3, 4, 5, 6, 7, 8, 9. You can see when we look at the values, we can see that these are the costs from the route to the actual node. So let's have a look and check that in the code. Again, we have our code for the uniform cost search. The only difference here is that the graph has changed to our example. So when we run this, we're going to use a for loop to check every node up to node 10, and you can see here we found the different nodes with the same costs. Now if we go back to our graph, you can see the costs that we calculated, and now if we paste the output from our program, you can see there's a problem. We have found nearly all the nodes except for one with the correct cost. But have a look at node 9. It says a cost of 12. Well, 4 plus 3 plus 5 is 12. But our minimum cost is 8. We've gone from 1 to 5 to 7 to 10 to 9. 2, 1, 2, 3. Which is a cost of 8, which is cheaper or shorter. So is the code wrong? So uniform cost search finds the shortest path. But does it? Let's have a look at the uniform cost search and the Dijkstra's algorithm. The uniform cost search does not guarantee that the first path found to a node is the shortest path. So our uniform cost search doesn't necessarily find the shortest path. It finds the shortest path when it first meets that node. So it can calculate the shortest path when it reaches a node. Is that what we want though? When we're finding efficiency, maybe that is if it's an infinite amount of nodes in a graph, because we never really know if there's going to be a shorter one. But perhaps the Dijkstra's algorithm is slightly more advanced than uniform cost search. Let's have a look. Here's our example with the Dijkstra algorithm on the left. We've changed the letters to numbers so we can apply the algorithm. So let's have a look. Okay, let's go back to our code. So we have our code here, and now we change the graph to our example using the Dijkstra's algorithm example, but we're using first of all the uniform cost search. So when we run that, we can see we visit the nodes and we found the cost correctly for nodes 2, 3, 5 and 6. But the result for node 4 says there's a cost of 4, not 3. The correct answer would be 3. We can see in our graph that we can get from 1 to 4 with a cost of 5, 1 to 4 with a cost of 4, so 1 and 3, but also we can go from node 1 to 3 to 5 to node 4, and that only has a cost of 3. So our uniform cost search finds node 4, calculates the minimum at that time. But because we've defined the graph as 4 going to 5, it hasn't seen that there's a shorter path from 1, 3, 5 to 4. So the uniform cost search is not the complete Dijkstra's algorithm. Let's have a look at that. We're going to use the Dijkstra's algorithm, but before we do, we're going to use an adjacency matrix in this algorithm. So just to explain, here we have a graph and you can see the matrix on the right. Now each node, we have the weight or the cost of the node going to another node. So node 1 going to node 2 has a cost of 3, to node 3 has a cost of 4, to node 4 has a cost of 2. And we do that for each node to make the adjacency matrix. So now let's see our Dijkstra's algorithm in the editor in Python code. So we're here, we have our code, which is the Dijkstra algorithm code, and here we've got our example graph that the uniform cost search didn't find the correct weight for node 4. So when we use the Dijkstra's algorithm, we can see that node 4 does indeed have the correct cost of 3, not 4. So the uniform cost search tells us the shortest path when it finds a node, but that's not always the shortest path. If you need to know the shortest path, you need to use the complete Dijkstra's algorithm that we have here. Well, that was a lot of information, wasn't it? Not only the uniform cost search, but all the Dijkstra's algorithm, adjacency matrix and priority queue. And if you did like that, we'd appreciate if you click the like, and if you haven't already, please subscribe.